In the last video in this series, we looked at the concept of center of mass, which is a point on an object that represents the average weighted position of all of the masses that make up that object. Importantly, it's the point where forces like gravity act on the object to move it linearly without causing the object to rotate. In this video, we will look at what happens when forces don't act at the object's center of mass. Consider this uniform rectangular beam. Since the beam is uniform and is symmetrical, its center of mass will be located at its geometric center. This means that half of the mass is located on the left side of the beam and half of the mass is located on the right side. If we were to place a support at the bottom of the beam at its center of mass, right in the middle, then the beam would be balanced and would not tip to either side of the support since the force due to gravity is acting right at this point. This structure would be akin to a seesaw, where the support is called the fulcrum or the pivot point, which is the part about which the structure member can rotate or pivot. Now, if we place a mass, say a person, on the left side of the seesaw, then the added mass of the person would cause an extra force to act down on the seesaw, but at some distance from its center. We'll call this distance r. This distance is also called the lever distance because it is a distance that gives the force leverage. This force is the weight of the person due to gravity and will cause the seesaw to pivot, in this case in an anti-clockwise direction about its center. Let's redraw our diagram as a free body diagram showing a force as a vector pointing downwards because gravity points downwards and at a lever distance r from the pivot point. The lever distance points in the direction from the pivot point to the force, which in this case is to the left. The extent that the force can cause an object to rotate about some pivot point is called torque, and it's given by the Greek letter tau and is defined as a lever distance multiplied by the force. Because torque is a product of force and distance, it has a unit of Newton meters. And the rotation occurs in the direction of the force relative to the pivot point. In this case, the force points down on the left of the pivot, so the initial rotation is anti-clockwise. One caveat to note is that the direction of the force vector and the lever distance must be 90 degrees to each other, or perpendicular to each other. So torque is a cross product of lever distance and force. If the force and the lever arm are not perpendicular to each other, then only the component of the force that is perpendicular to the lever does any rotating. The component of the force that is perpendicular can be found by taking the sine of the angle between them. In this case, the torque equation changes to being the product of the lever distance, the force, and the sine of the angle between them. If we rotate that force vector, we can see that its component that is perpendicular and the one that does the rotating reduces. Therefore, the torque reduces. When the force vector is aligned with the distance vector and points in the same direction, there is no longer a component of the force that is perpendicular, and so no rotation occurs. In this case, the angle between them is 180 degrees, and the sine of 180 is 0. Likewise, if the force points in the opposite direction as the distance vector, the angle between them is now 0 degrees, and the sine of 0 also equates to 0. So the force will not rotate the lever in this case either. So maximum torque occurs when the force vector and the lever distance vector are perpendicular to each other, and the torque is 0 when they are parallel to each other. So as torque is defined as a product of the perpendicular component of the force acting at some lever distance, then torque can be maximized in three ways. The first way is to ensure that the angle between the force and the lever arm vector is 90 degrees to each other or perpendicular, so that the sine of the angle between them is equal to 1, and the maximum amount of available force is used. The second is to increase the size of the force. If you double the force, you double the torque. Finally, the third way to maximize torque is to increase the lever arm distance. Conversely, for a given amount of torque required to rotate something, the force can be minimized by maximizing the lever distance and directing that force at 90 degrees to the lever arm. Let's take an example of changing a wheel on a car. To remove the wheel from the car, you need to loosen the lug nuts that hold the wheel in place using something like a tire wrench or a lug nut wrench. The pivot point is at the end of the wrench that is connected to the lug. The wrench handle is a lever arm, and the distance between the hand applying the force and the pivot point is a lever distance. To minimize the force needed, start by using the longest wrench available and apply the force right at the end of the wrench as far away from the pivot point as possible to maximize the lever distance. Finally, apply the force at a perpendicular angle to the wrench. So far, we've looked at torque created by a single force. There are times and applications, however, when there are multiple forces acting on an object to make it rotate. Sometimes these forces act in concert with each other to increase the torque, such as two hands on a steering wheel or multiple blades on a wind turbine. And sometimes they oppose each other, such as two children on a seesaw. When multiple forces are applied to a rigid body to rotate it, they are said to be coupled, and the net torque is the vector sum of the torque created by each individual force. So let's have a look at a numerical example. Consider a seesaw that is balanced on a support at its center, creating a pivot point at its center. Let's say the seesaw is 3 meters long, and two children jump on the seesaw. One has a mass of 25 kilograms and stands 1.5 meters from the support on the left side of the seesaw, while the other has a mass of 30 kilograms and stands 1 meter on the right side of the support. So, which way will the seesaw rotate? To find the answer, we need to determine the amount of torque created by each child. Since child 1 is on the left side of the seesaw, his weight will create a force that will push the left side downwards, resulting in a torque that is counterclockwise to the pivot point. Child 2 is on the right side of the seesaw, so the child's weight will push the right side downwards, resulting in a torque that is clockwise about the pivot point. The net torque will be the vector sum of these two torques. Let's first look at the torque created by child 1 on the left. Torque is defined as the cross product of the lever distance and force. Initially, the force vector points vertically downwards, and the lever distance vector points to the right. So the angle between them is 90 degrees, and the value of sine theta will be 1. The force created by his mass will be his weight, which is the product of his mass and the acceleration due to gravity. Substituting the values of 1.5 for lever distance 1, 25 kilograms for mass 1, and 9.8 kilograms meters per second squared for gravity, we get a torque of about 367 Newton meters. This torque is directed in the counterclockwise direction. We do the same for boy 2, where his lever distance is only 1 meters and his mass is 30 kilograms. And this gives us a torque of 294 Newton meters in the clockwise direction. The net torque will be the vector sum of these two torques. Since the two torques are in opposite directions, they will oppose each other. So let's define one direction to be positive, say counterclockwise, which means that the clockwise direction will be negative. So our net torque will be positive tau 1, since tau 1 rotates in a positive direction, minus tau 2, since tau 2 rotates in the negative direction. Putting the values gives us 367 Newton meters minus 294 Newton meters, or 73 Newton meters. The positive answer indicates that the net torque is in the positive counterclockwise direction. In other words, boy 1 produces a greater torque than boy 2, so his torque will dominate. Let's now consider a slightly different but related problem. Consider the left child standing at 1.5 meters from the center where the pivot is. Where does the second child have to stand on the right in order for the seesaw to be balanced? So in this situation, we want the net torque to be 0 so that there is no net rotation. This means that the clockwise torque from the right child must be equal to the counterclockwise torque produced by the left child. Again, let's take counterclockwise direction to be positive, so that tau 1 is positive and tau 2 is negative. Let's move tau1 to the right of the equation and eliminate the negative signs from both sides. Now, substitute the definition of torque with perpendicular distance times force. Finally, we can transpose this equation to solve for R2, which gives us R2 being equal to R1 multiplied by F1 and divided by F2. Now we can solve for R2 by substituting the values for R1, F1 and F2, noting that force here is the weight of the two children. This gives us a distance of 1.25 meters. So in order to balance the left child, who is standing 1.5 meters left of the pivot, the child on the right must stand 1.25 meters on the right of the pivot. Under this condition, the seesaw will not have any net torque and therefore no rotation in either direction. The last concept we'll talk about in this video is moments. Moments, from a mathematical perspective, is the same as torque. It's defined as a product of the force perpendicular to the distance from the pivot point. It has the same units of Newton meters. Torque and moment are often used interchangeably. So, if both have the same definition and their equations are the same, then why have two terms? Well, there are some slight differences in their use, particularly in mechanics. First, torque is applied in dynamic situations where rotation or turning movement occurs. Torque is a turning force and is a rotational equivalent to a linear force. A linear force causes an object to translate or move in a straight line in the direction of the force, while torque causes the object to rotate about some point in the direction of the force. Moment, on the other hand, is static and is a tendency for a force to cause a body to rotate without actually rotating it. Moments are used in many static applications to analyze bending and stress within the materials. Let's take a very simple example of a two-dimensional table consisting of a tabletop and two legs. The top is just sitting on top of the legs and not anchored to the legs in any way. Now, is there any torque happening here? No, because we don't see any rotation or movement. So it's static, not moving. But is there a moment? Yes. The reason is that the tabletop is supported by each of the two legs, but the center of mass of the table is in the middle. So the force of gravity, or its weight, will act at the center of mass of the tabletop. This causes a tendency to rotate about each of the legs. We can see this when we remove one of the legs and look at what happens. Let's remove the right leg. If we now put the right leg back, the tabletop would no longer rotate and it will be static again. But the same force and the same condition exists. So that force would have the tendency to rotate the tabletop about the left leg, but is prevented from doing so because of the right leg. The right leg produces a reaction that opposes the moment of the tabletop. We'll talk more about reactions in the next video. The table is static but experiences a moment due to the weight of the tabletop on the left leg. We could also consider the moment about the right leg by removing the left leg to produce a torque about the right leg. But since the left leg is there is no rotation because the left leg now produces a reaction against this moment. Instead, we have a weight at the center of the tabletop that causes a moment about both legs, and that could lead to bending or buckling over time. We'll talk more about bending moments in a later video. In summary, a torque is a rotation of a rigid body by a force that is acting perpendicular to the rotating arm or lever arm of that body at some distance from a point of pivot. It's defined as a product of the lever distance to the perpendicular force and has a unit of Newton meters. Torque is maximized when the angle between the force and the lever arm is 90 degrees with each other. Moment is similar to torque and is a tendency for a perpendicular force to cause rotation. Moment has the same definition as torque, that is, the distance multiplied by force. In physics, torque and moments have the same meaning and are used interchangeably. But in mechanics, they mean slightly different things. The main difference between torque and moment in mechanics is that torque is a dynamic force that causes rotation, while moment is a static force that does not cause any movement but a tendency to rotate.